Hello everyone, welcome to online lecture series of electronic devices. The subject code is KEC301. I am Dr. Sapna Katiyar, Professor in Electronics and Communication Engineering Department at ABES Institute of Technology, Ghaziabad. This is lecture number 21 and today's topic is breakdown mechanism and Zener diode. So in today's video lecture, I will discuss about the breakdown mechanism, where I will be discussing about the Zener breakdown, Avalanche breakdown and the second topic, which is the Zener diode. It means I am going to discuss about two topics. First is breakdown mechanism and second is Zener diode. So to understand the concept of Zener diode, first you need to understand in detail about the breakdown mechanism. What is it, how many types of breakdown mechanism and why actually it happens. So first let us begin with the breakdown mechanism. What is breakdown? From this particular term breakdown, the literal meaning you must be aware with. Breakdown is what? Every one of you can explain in your daily life in the general term very well. But what do you mean by the breakdown in case of the junction? See, in the previous lectures I have discussed about the PN junction diode. So what is the PN junction? If you recall, what is a PN junction? If you join a p-type semiconductor with a n-type semiconductor, so when you are joining these two semiconductors, so at the junction, there will be a junction, boundary in between these two, that is known as a PN junction, right? And in that particular PN junction, you can explain how that particular junction behaves, what is its characteristics, and in case of PN junction diode, how to apply the bias. How many types of bias are there? There are two basically types, forward bias and reverse bias. So you know it very well. In case of forward biased, how the batteries needs to be connected. P-type terminal or the anode or the p-type semiconductor, that particular type is being connected with the positive terminal of the battery and N is connected with the negative terminal of the battery. So that is the case of the forward bias. See what happens, there must be a situation when there is a condition of breakdown and that particular mechanism you can define as a breakdown mechanism. So how you can explain it in a basic term? Breakdown actually occurs in a reverse bias condition. When a reverse bias is applied to a PN junction. What do you mean by a reverse bias? See, if this is a PN junction, you can see if this is P, this is N, this is the PN junction. If P-type, this terminal is connected with the negative terminal of the battery and N is connected with the positive terminal of the battery in this manner. This is the situation of the reverse bias. Here what happened? In this particular case, in P-type, the majority charge carriers are holes, while in N-type, the majority charge carriers are electrons. So what happens over here? Holes, which are the majority charge carriers in P, they are attracted towards the negative terminal of the battery, and electrons, which are the majority charge carriers in N, they are attracted towards the positive terminal of the battery. So depletion width is increased in this particular case. Here depletion width is increased. So what happens if reverse bias is applied across a PN junction? And if you keep increasing this potential, if this particular potential, this you keep increasing, initially as per the value you are increasing to 2 from 1, then 3, 4, 5, 6. So what happens? If you keep increasing this potential, then a point will reach where junction breaks down. So that particular point where junction breakdowns, that voltage is known as a breakdown voltage. And at that particular point, when junction breakdowns, what will happen? When junction breakdowns, there will be a sharp increase in the current. So reverse current rises sharply. You know that there is a, in the case of when there is a if you are applying reverse bias across the junction, what is going to happen? In the case of the reverse bias condition, there are some minority charge carriers available in the semiconductors. Like in case of p-type semiconductor, what are the minority charge carriers? Electrons are the minority charge carriers, while in case of n, minority charge carriers are holes. Though majority charge carriers are moving away from the junction, but there will be a movement of the minority charge carriers across the junction. Now, current flows in this particular situation because of the minority charge carriers, and that current is known as a leakage current. So, you must remember this particular point. When the breakdown occurs, there is a sharp increase in the current, and that particular value of voltage where breakdown occurs, that is known as a breakdown voltage. See, as I have told you, in case of, if you talk about the Zener diode, the specific value of this reverse bias voltage, this is known as a breakdown voltage. It is denoted by Vz. You can plot this particular characteristic curve as well. You have studied the characteristic curve, the Vi characteristic curve of a junction diode. So, in case of forward bias, it is the same curve. There is a sharp increase in the current, and the value of the voltage, this value, this is known as a knee voltage. The value of this voltage is 0.7 if the semiconductor is used in silicon. The value of this particular voltage is 0.3 if the germanium is used for the manufacturing of this diode. Since we are talking about the breakdown mechanism, so how it behaves? When I am saying there is a breakdown at a particular voltage and there is a sharp increase in the current, so you can plot this particular line. Here you can say this is the condition of the reverse bias, this is reverse potential, voltage which is being applied in a reverse bias condition, current in the reverse bias. So, initially a very small amount of current flows, but after a certain time at a voltage, when the junction breaks down, this is the breakdown voltage, and you can see there is a sharp increase in current. Now, after this particular point, even if the voltage is being increased, there is no effect, like you can plot the characteristic curve into this particular manner. So, I hope now this particular point is clear. What do you understand by breakdown and how to define the breakdown voltage? See, there are two different types of mechanism. When we are talking about the breakdown, then two different mechanisms exist by which a PN junction breaks. Since we are talking about the breakdown, so the two conditions are known as a, first is the Zener breakdown and the second is the Avalanche breakdown. So, now at this particular point, breakdown is clear to you, but now let us understand what do you mean by Zener breakdown, what is Avalanche breakdown, what is the difference between these two, and how it behaves, like in which particular manner you are going to say, no, this is a Zener breakdown or this is the situation of the Avalanche breakdown. So, you must listen both the mechanisms in detail. Let us begin with the first one, which is the Zener breakdown. What is Zener breakdown? See, Zener breakdown phenomena, it occurs in a PN junction diode when heavy doping is being done. What is doping? Let me tell you once again, doping is what? Doping is the addition of impurity to a pure semiconductor. So, when a trivalent impurity is being added to a pure semiconductor, p-type semiconductor forms, and when pentavalent impurity is being added to a pure semiconductor, then n-type semiconductors is being formed, and the concentration, the amount of impurity which is being added to the pure semiconductor, on the basis of this, properties vary. See, so Zener breakdown, this phenomena occurs with a heavy doping, and when there is a heavy doping of the semiconductors, means large amount of impurities is being added to the pure semiconductor, then depletion layer will be thin. You can note down each and every point, heavily doping and thin depletion layer. So, in that particular case, Zener breakdown, this phenomena occurs. And here the thin depletion reason, it means more number of free electrons. At the same time, when you are applying reverse bias, then what will happen? Across the junction, electric field will establish, and that electric field which is being established across that particular depletion layer, that has a vital role in this breakdown mechanism. and the strength of electric field intensity will be high over here, and depends how much like the potential is being applied, and the electric field intensity which is being developed across the depletion region, the intensity of that electric field increases the kinetic energy of the free charge carriers, and when the kinetic energy of free charge carriers is being increased, it means now the charge carriers are capable and they can move from one region to the another region. They can jump from one region to the another region. So, this is how you can explain the Zener breakdown. What is the basic phenomena? So, here you must remember there is a vital role of the electric field intensity. Now, let us see how the energy band diagram you are going to plot in the case of the Zener breakdown. See, this is the Zener breakdown mechanism which you can explain with the help of the energy band diagram. See, a PN junction is being shown over here. This is the point of the junction. P-type semiconductor is being joined with the N-type semiconductor. Here you can see EV, this is the energy level for the valence band, EC is the energy level for the conduction band, EF is the Fermi level. So, you can see in case of P-type and in case of N-type, this valence band and the conduction bands, these two bands are not aligned. You can see the valence and conduction bands of P-type semiconductors are at relatively higher level in comparison to the N. Why it happens? We have already discussed in the previous lectures, but once again I will be telling you. This is because of the difference in the atomic structure of the P-type as well as the N-type. So, this is only because of this. That is why you have plotted, you can understand why there is a difference between the valence and conduction band. Now, you also know that in case of P-type semiconductor, the Fermi level, it lies close to the valence band, you can see over here. While in the case of N-type semiconductor, Fermi level is relatively close to the conduction band. So, this is being drawn like in this manner, you can understand from here. Now, what will happen? Here you can see that electrons which are available in the valence band of P-type semiconductor, they are tunneling into the conduction band of N-type. So, here you can observe there is a movement. The electrons are jumping from here to this region to this particular region. It means here these charge carriers collide with the atoms of P-type and N-type material, and now it produces the electron hole pairs. So, in the process of Zener breakdown, there is a creation of electron hole pair. And here when we are talking about the reverse current, when reverse current flows across the junction, you know this is because of the minority charge carriers, and because of which depletion region, when you are increasing the potential across that particular PN junction, already depletion layer is thin, and what is going to happen? Now, depletion layer will be completely vanishes, and this particular process is known as a Zener breakdown, right? So, I hope now this particular point is clear what is Zener breakdown, and in the case of this Zener breakdown, it is not going to impact the quality of the diode. You cannot say that if this particular breakdown occurs, then that particular component is going to be damaged. It is not like always following. So, you can understand the Zener breakdown mechanism with the help of the energy band diagram also, right. Now, Zener breakdown can be observed in case of Zener diodes, and the value of this potential is very important. It can be observed in between 5 to 8 volt, but sometimes it can be observed less than 5 volt, right. See, whenever there is a manufacturing of a diode, so it totally depends upon the manufacturer if we would like to change the breakdown voltage, that can also be changed depending upon the doping level and the other things, and it can be totally done by the manufacturer. See, you can see this particular curve where breakdown voltage is being shown over here. This is the reverse voltage because we are talking about the reverse bias condition. So, VR is the voltage which is being applied across the PN junction in a reverse bias condition. Current which is flowing over here, you can see initially a small amount of current flows which is known as a reverse saturation current I0, and this is because of the minority charge carriers. When you keep increasing voltage, then what will happen? At a certain point, breakdown will occur, and this particular voltage is general, can be denoted as VB. So, this is a Zener breakdown. You can see after this particular voltage, the current increases sharply. So, this is the ideal characteristic, but if you would like to draw the practical curve, there will be a little, very slightly slope over here. See, Zener breakdown does not result in damaging a diode. As I have told you, it does not mean the diode is going to be damaged. Since current is only due to the drifting of electrons, it means there is a limit as well, right? Limit can also be set over here. So, this is all about the Zener breakdown. Now, let us discuss about the avalanche breakdown. Avalanche breakdown is the second type of breakdown mechanism. What is avalanche breakdown? Avalanche breakdown occurs, it also occurs in the p-n junction condition, but here you must remember that here the doping is moderately done. When the doping is moderate, it means now the depletion layer will be relatively thick. If you compare the Zener and the avalanche one, so here you can see that the depletion layer is relatively thick. When you are going to increase the reverse bias, means the potential you are going to increase, then electric field across the depletion region will also vary, and because of that there is a change in the velocity of the charge carriers, and that particular charge carriers which are crossing the depletion layers, that particular concentration will increase. So, here what is happening? These charge carriers are going to collide with the atoms of that particular crystal, and they are going to impart some of their kinetic energy to the valence electrons, and now these valence electrons will break covalent bonds, and when more and more number of free electrons are available, means this is a kind of multiplication process. Now, when they are available in more amount, they jump into the conduction band, and now they are free for the conduction. So, since one electron is going to collide with one atom, 2 will be released, and accordingly multiplication takes place. So, this is in this particular process avalanche multiplication takes place. Now, what happens? As I have told you, newly generated free electrons, those which are available, they will be accelerated. When they will be accelerated, they will collide with the other atom, and the process continues. As I have told you, this is the carrier multiplication. And here electric field becomes very high. It means now reverse current start flowing through the diode, and then avalanche breakdown occurs. So, this is the situation of the avalanche breakdown. Here more number of charge carriers are available, and they are colliding, they are transferring their kinetic energy to the others. Like in this particular manner, you can explain the avalanche breakdown. Now, avalanche breakdown can be observed in a Zener diode, but here the voltage is greater than 8 volt. In the case of the Zener breakdown, the voltage is in between 5 to 8 volt or less than 5 volt, but it can be observed at a voltage greater than 8 volt. You can see the curve, same. Avalanche breakdown occurs later, but Zener. So, you can say Zener breakdown occurs first, then the avalanche. As I have told you, it occurs more than 8 volt. So, this is the breakdown voltage for avalanche breakdown, and this is the breakdown voltage for the Zener breakdown. See, it usually occurs when high reverse voltage is applied, and if we increase applied reverse voltage, electric field across the junction will keep increasing and breakdown will occur. Right. So, this is how you can explain the avalanche breakdown. Comparison between the Zener and avalanche. How to differentiate between these two? All the points are very simple. You can explain it very nicely. See, depletion width is thin in case of Zener diode. In case of avalanche, this is thick. Here electric field is strong. In case of Zener breakdown, here electric field is weak. Depletion region is thin. It means doping is heavy, while here doping is low. Here reverse potential is low, here reverse potential is high, because it occurs more than 8 volt. In the case of Zener breakdown, ionization is due to the electric field. In the case of avalanche breakdown, ionization is due to the collision. As I have told you about the breakdown voltage in between 5 to 8 volt, here greater than 8 volt. Here breakdown voltage decreases when the temperature increases, means it is a negative temperature coefficient. Here breakdown voltage increases when the temperature increases, it means positive temperature coefficient. So, this is how you can differentiate the Zener breakdown with the Avalanche one. You must note down this particular table, this is very important one. Now, let us discuss about the second topic of today's video lecture, which is about the Zener diode. See, at this particular point, it is very much clear to you what is Zener breakdown, what is Avalanche. So, now let us discuss about the Zener diode. Zener diode is also known as a breakdown diodes, because for this breakdown mechanism we have already discussed, and it happens in the case of the heavily doped semiconductor devices, and the name Zener diode was like being fixed on the basis of the name of the scientist who has developed this, American scientist Clarence Melvin Zener. He has discovered the Zener effect. This is the circuit symbol for the Zener diode. Zener diode is also a two-terminal device, anode and cathode. You must remember this particular bar, this shows the negative terminal, the cathode one. So, anode and cathode. So, this is the circuit symbol. Whenever there is a requirement to draw in a circuit, you must draw in this particular manner. See, as I have told you, breakdown voltage in a case of a Zener diode can be set by the manufacturer. Zener diodes are the basic building blocks in the electronic circuitries. They are widely used, and a very common application of a Zener diode is in the case of the voltage regulator. Zener diodes are commonly used to protect electronic circuitries from over voltage. So, there are various applications of the Zener diodes as well. Now, let us discuss about the VI characteristic. See, VI characteristics of a Zener diode, again it can be divided into two cases, forward characteristic and the reverse characteristic. You know that it is especially designed to operate in a reverse bias condition. So, if you have to plot the forward characteristic, that is quite similar to the PN junction diode, and the reverse bias characteristic I have already explained you in the case of the breakdown mechanism. When you are increasing the reverse voltage, initially a small amount of reverse saturation current flows, which is I naught, and this is because of the minority charge carriers. But at a certain voltage, if you keep increasing the reverse voltage, then at a certain voltage reverse current increases suddenly and very sharply, and this is the indication of the breakdown. And this particular breakdown voltage is known as a Zener breakdown voltage, and commonly it is denoted by Vz. So, this is how you can explain the VI characteristics in two bias, in the forward characteristic and the reverse characteristic. Now, let us draw how it looks like. See, this is the forward bias condition. The characteristic curve is almost similar to the PN junction diode. This is the reverse bias condition where the Zener diode operates, and it looks like, you can see this is the breakdown voltage, Zener breakdown voltage Vz, and here you can see this curve, the current increases sharply and suddenly, right? But you practically you cannot see this particular line as a straight line, there is a relative slope over there. So, this is how you can draw the VI characteristic. But what is this Zener region? You can see this particular region. This is the Zener region. What is its importance? What is its significance? See, reverse breakdown of Zener diode, it operates in this particular region, which is known as a Zener region, as it is being shown in this particular diagram. And here you can observe that the voltage, this particular value of voltage is fixed. So, here voltage across the Zener diode remains constant. Now, this particular voltage is fixed, but current changes, and depending upon the value of this current changes depending upon the supply voltage, right? And Zener diode is operated in this region when it is being used as a voltage regulator. What is the use of a regulator? You can set like the speed of the fan, you can set the your requirements on the basis of that particular thing. Even if there is an increase in the input, supply, output remains fixed. I will discuss the Zener diode as a voltage regulator in the next video lecture. So, this is how you can plot the VI characteristic curve. Some of the important specifications. See, Zener diode, as I have told you, depending upon the construction, manufacturer can set the value of the breakdown voltage. So, Zener diode vary in specifications like working voltage, power dissipation, maximum reverse current, minimum Zener current. But what are these parameters? See, voltage Vz, this is the breakdown voltage, and it varies from minus 2.4 volt to about 200 volt. Current Iz maximum, Zener current maximum and current Iz minimum. What is the maximum and minimum value? The rated maximum and minimum values are 200 microampere to 200 ampere, and minimum value is about 5 milliampere to 10 milliampere. Power dissipation. How to calculate the power dissipation? This is the product of Vz into Iz, Zener voltage, breakdown voltage into Zener current, and its value ranges from 150 milliwatt to 50 watt. Zener resistance, you can also calculate how much resistance it is going to offer. So, from the Ohm's law, V is equal to IR, you can calculate the resistance. So, resistance is what? Voltage upon current. Voltage tolerance, typically plus minus 5%. Temperature stability means diode around 5 volt have the best stability. So, these are all the important factors, the specifications which you must remember, right? Now, let us discuss what are the advantages, disadvantages and applications. Why to study Zener diode? Why to utilize it? See, some of the important advantages of the Zener diode. Power dissipation capacity is very high. This is why it is commonly used. High accuracy, small size and low cost. So, all these factors are very important. Cost is low, size is small, it gives high accuracy, at the same time power dissipation capacity is very high. So, these are the major applications. Disadvantages, like major utilities why the Zener diode is being used. Low efficiency, if there is a heavy current, heavy load current, its efficiency is relatively low. So, that is like limitation in the case of the Zener diode. Poor regulation ratio, leakage current is high. So, these are the certain disadvantages of the Zener diode. Now, let us discuss what are the applications of Zener diode. It is normally used as a voltage reference, voltage stabilizers or shunt regulators, in switching operations, in clipping circuits, in clamping circuits, in various protection circuits. And so many applications also exist beyond this particular list. Here I have listed 5 applications, but there are a huge number of lists where the Zener diodes can be successfully used. So, you can note down all of these points, these are very important points. So, in today's lecture, I have discussed about the breakdown mechanism. First is the Zener breakdown, second is the Avalanche breakdown, and then I have discussed about the Zener diode, its VI characteristics, applications, advantages and disadvantages. I hope all of these topics are clear to you. Thank you so much for watching this video.